Have you ever wondered what gives the universe its mass? Sounds like the beginning of a sci-fi story, doesn't it? But no, this is firmly grounded in real physics. And actually, it takes us right to one of the most significant discoveries in modern science, something you've probably heard being hyped as the God particle. Yes, I'm talking about the Higgs boson, but just to set the record straight, that nickname is ridiculously misleading. It's not divine, nor does it hold some supernatural status. It's just physics, beautiful and complex, yet nothing mystical. So, before we dive in, I need to give you a vibe check on why this topic is fascinating, but also criminally misunderstood. The Higgs boson isn't just a subatomic particle. It's an encapsulation of a fundamental mechanism underlying reality. Think about it. Everything from your morning coffee to giant black holes, they all owe some aspect of their existence to what scientists call the Higgs field. Intrigued yet? Or am I nerding out too much? All right, let's decode this idea starting with a deceptively simple-seeming question. Where does mass come from? This is where the standard model of particle physics, the incredibly successful theory that describes the fundamental particles and forces, comes in. But despite its successes, for decades it carried an unresolved issue. Elementary particles, like electrons, are supposed to have mass, but the equations of the standard model initially implied that they should be massless. That's a problem when you want to describe a universe with tangible stuff, like people, planets, pineapple pizzas. Cue Peter Higgs and colleagues in the 1960s, who theorized something audacious. Another field permeates the cosmos, one unlike anything we'd conceived of before. Imagine an invisible medium everywhere, sort of like a cosmic molasses. This is the Higgs field. Now, particles moving through this field aren't all affected equally. The Higgs field interacts with some particles and resists their motion, essentially slowing them down, and that resistance manifests as mass. It's like if you walk through water, you feel its resistance and it slows you down. A particle's likelihood of interacting with the Higgs field determines its mass. Simple particles like photons glide through unaffected, which is why they stay massless. But something heavier, like a W boson, that's like trying to run through honey. But wait, you might ask, if the Higgs field has always been there, why did it take so long to find the Higgs boson? Excellent question. This field is everywhere, yes, but detecting the particle, a boson, is a different game entirely. That's because bosons are excitations, or ripples, in the field. And this boson, in particular, is extraordinarily elusive. It took decades of scientific and financial investment, and the combined effort of literally thousands of physicists to pin it down. As most of you probably know, the big breakthrough came in 2012 at the Large Hadron Collider, or LHC, in Switzerland. This enormous machine smashes protons together at speeds close to that of light. Why? The LHC was essentially designed to recreate conditions just after the Big Bang, moments when the universe was hot enough for Higgs bosons to briefly appear. Picture two cars crashing together in a junkyard, revealing their parts upon impact. Similarly, the LHC creates controlled chaos, and in the aftermath, scientists saw evidence of this long-theorized particle. The announcement of the discovery made headlines worldwide because it confirmed a cornerstone of particle physics. Now let's lift the hood up and take a closer look at what we've learned since then. The Higgs particle has a mass of about 125 giga-electron-volts, roughly 125 times the mass of a proton. It's also ridiculously unstable, breaking down into lighter particles almost immediately after it forms. Studying its decay patterns has kept physicists up at night because it opens doors to questions like, what lies beyond the standard model? In fact, one pivotal mystery the Higgs boson leaves us with is its own mass. It's almost suspiciously lightweight. According to quantum mechanics, it should be far more massive unless odd cancellations involving yet unknown particles are happening. Some physicists argue this hints at new physics we haven't uncovered yet. like supersymmetry, which hypothesizes additional particles. And here's where I might ruffle some feathers. Despite the hype, discovering the Higgs boson is not an end. It's the beginning of an entirely new chapter. There's a lot we don't understand, starting with how the Higgs field came to exist moments after the Big Bang. Without the field activating itself, so to speak, particles would have remained massless. Space, time would look drastically different, devoid of galaxies and gravity. This makes the Higgs mechanism not just a bystander in physics, but a primary driver of the universe's operability. Another mind-bender. What role does the Higgs boson play in the multiverse debate? Some argue that its properties might hint at why our universe's fundamental constants, things like the strength of gravity and the speed of light, are fine-tuned for life. It raises the philosophical idea of anthropic reasoning, though most physicists, myself included, find that unsatisfying. If this so-called multiverse exists, theoretical particle behaviors in these other universes might offer radically different laws, not just limiting life, but maybe making them entirely incomprehensible. Now bring in cosmology for a second. Turns out, the Higgs field might connect to another troubling question: dark energy. Recent work attempts to link the Higgs field with this mysterious force tearing the universe apart. Is this connection plausible? Maybe. Is it proven? Absolutely not. But hey, welcome to Frontier Physics. You're grappling with things literally no one on Earth fully understands yet. But let's pump the brakes. What about all this God particle stuff? Isn't God a bit much? Well, here's a fun behind-the-scenes tidbit. Leon Lederman, a physicist, coined it the God particle in his book title, except he really wanted to call it the goddamn particle because it was so hard to detect. Editors made it snappier. It stuck. Flash forward to today, and I'm constantly shaking my head at how misunderstood this nickname makes the Higgs sound. In conclusion, while the Higgs boson solves one piece of a very complicated puzzle, it's far from the big picture in physics. We've got so much left to learn: where the Higgs field originated, how it interacts with other forces, and whether it carries deeper implications for theories like quantum gravity or our ultimate quest for a theory of everything. If this captivated you, share in the comments. What's your take on the Higgs field's wider implications? Give this video a thumbs up, and most importantly, click that subscribe button to join me in unraveling more of the universe's deeply hidden truths. And stay hyper-focused and let quantum fields guide your curiosity.